So that's kind of fun. So I've shown you some examples of things that are vector spaces. Let's look at a couple examples of things that are not vector spaces. Not vector spaces. And then we'll stop here and then pick up with subspaces. I'm not going to do all of these examples that I have here. I'm just going to pick out a few. I'm going to actually do one that's not on there first. So let V equal all points x, y, right, where x, y are real, such that x and y are both greater than or equal to 0. With standard addition and scalar multiplication. So this is an example of something that is not a vector space. So show that it's not a vector space. So x and y are real numbers. So x and y are real numbers. So this is a set of points in R squared. X and y are real numbers, and x and y are both greater than or equal to 0. And I'm going to show that B is not a vector space. Show that V is not a vector space. Well, let's just kind of go through some of the axioms here, right? Let's go through the first axiom. So the first one, if we look at the first one, we have u plus v is in V, right? So we have to pick a vector that's in my set, right? So that means that I need to come up with a point, and I'm just going to write it in vector form, so that x and y are both greater than or equal to 0. So I can use 4 and 2. These both are greater than or equal to 0. And I'll choose 3 and 1. Okay? And these guys are both greater than or equal to 0. Now, I cannot choose -3 or -1, right? Because then that would break this condition that I have on my set, right? What happens when I add these two together, right? So this is the first one. What happens when I add two of these vectors together, these two vectors together, right, that satisfy this condition? Do I end up with a vector whose x and y values are greater than or equal to 1? And if since this is standard addition and scalar multiplication, I can just do what I have normally done. So I get 7, 3. 7 is not negative. 3 is not negative. So u plus v, when I look at it, u plus v is going to satisfy the condition that x and y are greater than or equal to 0, as long as u and v have that condition. And you can never come up with a situation where you add two positive numbers together, right, using standard addition and get a negative number, right? That never happens. There's no way that you can add two positive numbers together using standard regular addition and get a negative number. And so that's what we're seeing right here with number 1. So number 1 is fine. There's no issues with it. Axiom 1 is perfectly fine. So I can say axiom 1 holds. Let's look at axiom 2, right? Let's look at axiom 2. When I multiply a scalar times a vector that's in this set, right, will I get a vector, or if I multiply a scalar times an object that's in this set, will I get an object back in that set? And sometimes you'll say, yeah, of course you will. Of course you will. But let's look at that. Okay, I'll use my same u, so I'll let my c equal, what's a good one? No, 3. Okay. So I say, okay, that'd be 3 times 4, 2. And that is 12, 6. And you say, okay, 4 coming 2, these both are positive, right? None of these guys are negative, right? I multiplied by a scalar, got something that wasn't negative 2. And you're like, okay, I can go to axiom 2, axiom 3 now. This one holds, axiom 2 holds. But no, hold up. What did you just do here? You chose your C to be positive. But does C have to be positive? And the answer is no. There is no restriction on your real numbers. Your real numbers could be anything they want to be. The only restrictions are on the vector itself, on the objects that we have in V. But there's no restriction on C. So I can actually choose C to be a different value than a positive value. What's a good value to check out? Well, let's just do C equal to -2. If I choose C equal to -2 and multiply it times U, what do I get? I get -8, -4. Well, guess what? -8, -4, both of these guys are outside of this set, right? -8 is definitely less than 0, and -4 is definitely less than 0. Both my x and my y values are less than 0. This means that this axiom fails. Axiom 2 fails. Another axiom that fails, I'm not going to go through all of them, but another axiom that fails is axiom number 6. Axiom number 6 fails because I need to find out what is negative U. So if I know what U is, what would be, so what's the 0 vector for this set? The 0 vector for this set will still be 0, 0, right? Because when you add 0, 0 to U, right, I get back 4, 2. But what would be the negative U of 4, 2? You will have to say it's -4, -2, but -4, -2 is outside the set. So axiom 6 is also going to fail. Okay. So axiom 6 fails and axiom 2 fails, right? Because we don't have any negative values in our set. Okay. Let's look at one more, and then we'll stop here. Like I said before, I just want you guys to see it. I'm not going to go into super detail like I would in class because I will test you guys over it. But I do want you to see it so that you've seen it and have a kind of an idea of what's going on. Let's do one more. If I can pop off the top. I just do the first one that I have on the PowerPoint. No, I'll do the last one. Let V equal P2, so polynomials of degree 2 or less, with addition. And I'm going to have to write here that A1 x squared plus B1x plus C1 plus A2 x squared plus B2x plus C2. I'm going to have to put a plus sign in between. I'm trying not to erase anything, so I apologize. This is equal to A1, A2 x squared plus B1, B2x plus C1, C2. So essentially when I do addition of these two guys, when I do addition of these two polynomials, essentially what I'm going to do is end up multiplying their coefficients together. And then scalar multiplication. So suppose I have k times a1x squared, or I just say use a, k times a, x squared plus bx plus c, and I'll put the little dot here. This is equal to, what do I have? Looking at the wrong thing. Oh, it's just regular scalar multiplication. So it becomes ka x squared plus kbx plus kc. And I want to show that this is not a vector space as well. Okay, I'm going to erase this. Okay, notice that I've changed the addition, right? But the scalar multiplication has stayed the same. So that B is not a vector space. Okay. Now, whenever a problem changes the addition or the scalar multiplication, it's probably best to start looking at the axioms that deal with addition and scalar multiplication. Okay? Look at the axioms that deal with addition and scalar multiplication. Those axioms are like 1, 2, 3, 4, 7, 8, 9, 10. Okay? All of these axioms deal with scalar multiplication. I'm not going to choose 1 and 2. You can try it out for yourself. What we would need to see is that if I have a polynomial of degree 2 or less and add it to a polynomial of degree 2 or less, do I end up with a polynomial of degree 2 or less? And the answer is yes, I do, even with this strange addition that I have. If I do scalar times a polynomial of degree 2 or less, do I end up with a polynomial of degree 2 or less? And the answer is yes, even with this scalar multiplication that I have. It doesn't matter in which order I do the addition. It doesn't matter in which order I do, and it doesn't matter in which order, how many polynomial terms I have. If I have a third polynomial and add them together, it won't change the fact at all. 5 and 6 might be an issue, but I'm not going to worry about that. I'm going to pick a different one actually. So I'm gonna choose like this one right here. I'm going to choose axiom 7. Now, why am I choosing 7? Well, because again, I have this strange addition, right? And I want to see if this strange addition has screwed up this equality between the two. So I want to look at axiom 7. Okay. So let's pick a C here. I'll let my C be 2. I'll let U be something simple. 3x squared plus 4x. Okay. And I'll let B equal 2x squared plus 6x minus 1. Okay. So let's look at C times U plus B. Now we have to be careful here when we do this. When we do C times U plus B, this is what's happened. This becomes a red plus, right? This is a multiplication right here. C times U plus B. Here, so I have 2. Then I have the quantity, 3x squared plus 4x plus 0, essentially is what I have here. Then I have 2x squared plus 6x minus 1. Now I haven't actually tried this and see if it actually gives me the same thing or not. I might actually get this to be equal. We're going to find out in just a second. Okay. Remember to do what you always do. Please excuse my dear Aunt Sally. I'm looking at the left side of axiom 7 right now. I'm going to see if the left side equals the right side. Left side. Okay. So let's do the addition first. If I add these two together, remember by that addition I multiply the coefficients together, so this would be 3 times 2, so it gives me 6x squared. 4 times 6, that gives me 24x. 0 times -1, that gives me 0. And then last but not least, I do 2 times this matrix. I get 12x squared plus 48x plus a 0. Now let's try out the next one. And again, this one might actually work out. I'm not really sure. Right side. C times U plus C times V. So the time goes between each one of these guys. Addition goes here. Yep. So it's 2 times the quantity, 3x squared plus 4x plus 2 times the quantity, 2x squared plus 6x minus 1. Dot here, plus. Okay. Again, please excuse my direct salads. I'm going to do multiplication right before I do the addition. So 2 times this, I get 6x squared, right? Plus, what's that? 8x. Here, when I multiply this, I get 4x squared plus 12x minus 2. I'll put parentheses around it. Then I'll add. Okay. And now I do addition. So now I do addition, multiplying the coefficients together. So 6 times 4, that's 24 x squared. 8 times 12, what's that, 96 x. This is a 0 times -2, so I get 0. And this is what I have. Now, the question is, do these guys match? Are they equal? And the answer is they're not equal. So axiom 7 fails. Axiom 7 fails. So here I was able, since axiom 7 fails, that means that this cannot be a vector space, right? So anyway, just to kind of give you an idea of how I can show that something is not a vector space. I could show this in general without using actual polynomials with real numbers. I could just have arbitrary numbers, ax squared plus bx plus c. But I wanted to show it to you with numbers because sometimes it's easier to get an idea of what's going on when you have numbers to look at. Alrighty then, I think that is it for this lecture. We're going to pick up with subspaces and talk a little bit about that, and then we'll be done with linear algebra. All right, talk to you guys later. Bye.